So I think I just wanted to start with the assignment 7 write-up really quick, since I wanted to talk about that last time, but I kind of gave a little bit of an extension. So the first one we had was what line of code makes the bucket class abstract? And from the code, I already pulled it up. That would be this line right here. So pure virtual and abstract are the same thing, C++, right? They use that word pure virtual because there's no real word abstract in C++, but right, to mark it abstract, you just set it equal to 0, so it would be this one right here. And if you have any abstract function, then it makes the class that it's in abstract as well in C++. Okay, so I think most people got that one. So the second one, we have these template bucket classes are equipped to store any type. Unfortunately, bucket sort may not always work with custom data types. What operator overload is required for custom types so that sort will work? And that would be, so consider that when we sort something, so I got either people had the right idea or were maybe thinking of the operator overload in this program. And I guess the thing is, you didn't actually have to write the operator overload for assignment 7. I guess I should keep the question on this one. You actually have to write the operator overload that was required to do this. And then the reason that being is that we didn't actually have to sort any custom types. So you had a bucket that stored integers, characters, floats, and strings. And all of those are primitive data types. Save for strings in C++, I guess, that is a class that you have to like import. But the rest of those are like primitives, they're built into the language. So they're already sortable by default. And so the answer I got was either the correct one, or I got a lot of people saying that the operator overload from the program, which was this one, the indexer overload, was the one that was required, and that's not necessarily true. So for the bucket, right, what it had was a R, which was, I guess, actually a pointer, but let's just keep it like that for now. So it was some sort of array. And so if that was private, yes, I did have to use the indexer operator to actually access things. But if I made like a accessor, that would do the same thing too, right? So if I said like get R, or if I had a get at that like took an index, so that took like the int, some int I that just went in there and did the same thing as the indexer, then I don't necessarily need the indexer to be overloaded. It's just there for convenience. Now the thing that is required for sorting, and specifically custom data types, which we didn't again do in this program. So let's say I had like the fraction class that I gave a few lectures ago, and we wrote an overload that allowed us to sort that in a template. What we needed was, and you could say any one of these or any combination. Actually, any guesses on this one? So if it's not the indexer, because we have other ways to access, right? Then if you're thinking about bubble sort, what is the exact? Actually, you know what? Now that I think about it, I guess the accessor is somewhat required, but I guess we could always pass the array. So I'm still gonna say no on that one. Anyways, I digress. What operators might you actually need in order to sort? So what do you think might be shared across all sorting algorithms, or at least most sorting algorithms that we would write? I know a fair amount of you got it. Yeah, exactly. So any of the comparison operators, right? The less than, greater than, less than equal to, greater than equal to, right? Less than, greater than. So all of the inequality comparison operators specifically. Yeah, you're both right. Right. And the reason being, we have to check if things are in the right order in order to sort them. At least when we do comparison sorting, like bubble sort, selection sort, merge sort, quicksort, that kind of stuff. We have to have those. So the indexer we can get around if we just give ourselves an accessor that actually returns the array, and then we can pass that into the sort method. And the sort function, I guess, itself already had, or no, it was in the garbage processor class, right? So it did have to index it, but I suppose we could always rewrite it so that it would pass an array. The most important part to a sorting part is the actual ability to do a comparison for these custom classes. And that, I guess the other argument for why it wasn't this would be the fact that we're not sorting the bucket, and this is a bucket operator. We're sorting the things in the bucket, and in order to compare the things in the bucket, we need to have a comparison, if that makes sense. So just wanted to clear that up because I got that question a fair amount, or that response a fair amount, in the write-up. Right, so number 3, what constructor can you initialize a type variable to some default value? Right, so that would be the type constructor itself. So that one. And specifically, if I have some template class T, or it was called type in this program, then whatever the constructor of T is. So the default constructor of T. So number 4, the isType function in garbage processor and swap function in bucket are all static. Why do you think that is? And I don't remember. I got one answer quite often, and I don't quite remember what it was. But the correct answer on this one would be the fact that we don't need an object instance if we make it static. So I don't necessarily need a bucket to swap things, or at least I shouldn't necessarily require that, which is why it's static. I definitely could, but I think it would make more sense to not require that. And isType the same thing. So if I wanted to get like isInteger or isCharacter or any of that, then I don't think that relies on any of the members of garbage processor, and it would probably not be helpful to like have to require you to have a garbage processor class instance in order to use it. So helper functions like that kind of just operate on their own, that really you could put at a global scope and kind of get away with it. We can put into a class and make them static, and then it's a little more organized, but we don't have to tie it to an instance reference. And then number 5, why is max size in static bucket static? And that's pretty much a similar thing here. It's shared across all of the instances of a static bucket, so we don't want it to belong to any one specific instance. We all want them to share that same max size, which you could have made a constant, and I got a couple answers about constants, but it isn't strictly a constant here in the program, even though I told some of you to make it a constant, and it should be a constant. The static part has to do with the fact that we want it to be shared across all of them. So it can possibly change, but we probably shouldn't do that, but the key here is the fact that it's shared across all of them. So any questions on those parts? Okay. Close that then. So 2 more things, I guess, before we talk about the review. First thing, let me do this one first because it's shorter. I posted this announcement last week. It's just, we might have a little bit of extra time. I know I talked about this last class. We might have a little bit of extra time at the end of the semester because I think we only really have one more topic to cover. And then I'll probably only take about 1 lecture, maybe a lecture and a half to talk about. So we might have 1 lecture, half a lecture, something like that left over in terms of time. So I've put some topics here that we could maybe talk about if we happen to have that free time, which I think we will. But there's a few here. So there's time complexity, which is basically how do we measure the runtime of an algorithm without having to have it dependent on like actual real time. So we don't measure it in seconds or milliseconds because that's kind of dependent on the actual processor that you're running it on and the resources that you have, and like some operating system conditions. So it's kind of inconsistent. So it's how do we measure it in terms of how many steps does it take to solve a problem. Merge sort and quicksort here are really popular sorting algorithms. They're probably the most common that you'll see. You'll learn them in 302 as well. I guess these are just there as a like head start for some of the other classes that you might be taking. So time complexity is part of 302. Merge sort and quicksort are part of 302, and that's a sorting algorithm that uses recursion. We have threading and concurrent programming, which is pretty popular, but usually you don't have to think about it too much, which is just basically parallel processing, even though that's not always the case. It's basically being able to run multiple parts of your code at the same time and then kind of have them join back together and then work together. That way you can speed up your program by having, things that you can have run at the same time. In other words, concurrently run at the same time. The next one we have was application development, which I'm kind of iffy on that one, just because it would take quite a while to talk about. We'd have to talk about the API and all that stuff. So I am a little bit iffy on this one, even though I did put it as an example. Kind of depends on how much free time we end up having, if that one ends up working out or not. But that would just be development of like mobile apps. Games, which we would have to decide on something to talk about there, or something like Windows Forms, which you can make, like Windows programs in with graphical user interface. And if you all are interested in that, we are planning, once this whole pandemic thing passes by, we were planning on having an app development club on campus with Dr. Fonseca, and I think I was supposed to help with it just because I do application development normally. So if you're interested in mobile app development specifically, in the near future we might actually have that, and it will be in C#. And I'll probably provide a library for you. I might even just post it if you really want it, because I've written a library that helps with that already. Right, and then the last one I just kind of threw in there, which was lambda expressions, and I don't think that would be long enough to cover anything, but I do put it out there, which is just kind of pieces of code that aren't bound to any sort of specific function. You just throw them out there and kind of write them in curly braces, and they just exist one time and get copied, and they're there. Right, so if you have time, please leave a comment on this thread. It's on Canvas. It's an announcement from November 4th. I know it's probably small. You can't see it. So just leave a comment there if there's any specific topic you want to talk about, and I will think about it, depending on how much time we have. And then, maybe if I don't have time to talk about the application development, because I am seeing that a few people are asking about that, and maybe I'll talk about it over winter and just put it on the YouTube channel or something if you're interested. Right, so take a look at that if you have time. If not, not a big deal. And then I think the last thing I wanted to talk about for maybe 2 or 3 minutes here was just the exceptions. Oh, and whatever talk we end up doing, so sorry, I should have clarified. So this is just, if we have extra time, this is just some random topic to fill that time, so that, if you don't want to come to class, you don't have to come to class, but if you still want to, talk about something academic, then we can discuss that and not have it be something you have to worry about on the final. So just some topic to either prepare you for another CS class, or to, enrich, whatever talking point I can throw out there. Just something academic to talk about. Yeah, but it wouldn't be on the final. Just there for fun, I guess. I've put that in quotation marks, fun. Learning is fun, guys. Right, what I wanted to do is address some of the exceptions, just because I realized, so I gave this whole list of things on the exception assignment. I posted this link on the assignment 7, 8? 8's the exception handling one, right? I posted this on the assignment 8 Canvas post, just so that you would have a list of the exceptions. I didn't realize, I guess I didn't read it all that much, that it doesn't really explain what they are for the most part, and so I wanted to clear that up a little bit just because I know there was some questions on this assignment in general, and I think it might be good to know some of these at least so that you have them for the future and so that you can also maybe have them for the test and for the write-up. So the exception class, right, we talked about this one, is just the basic exception class. It's the parent to all of these other ones. So if I was to, go in that class hierarchy, then I'm going to have the exception class. I know it's lowercase in C++, but exception class, and then we have things derived from that. So we'll have like length error and the bad alloc and all of that are all... These are all derived classes from exception. So they're all examples of exception, which is why when you do a catch and if you put exception, it will always catch any of those no matter what. Even if you didn't specifically put bad allocation or length error or whatever, it will catch it because those are examples of exception. So it'll do that whole upcasting thing that we talked about, right? So remember that we had something like this where I was allowed to... first couple weeks of class for inheriting, I was allowed to do something like this where I could say obj is equal to player, and that was fine because a player is a example of a game object, right? So a player would be lower down inheriting from this, right? So player is here, and if it points upwards, we said that was like an example of something. So this is a relationship. So here the length error is an exception, the bad alloc is an exception, so if you catch just an exception, it will catch those. So it'll do some sort of upcasting up that class hierarchy. Right, so all of these are examples of exceptions. So when you throw them, they'll get caught as exceptions unless you specifically handle them, which is important to consider. So the ones that we had in this assignment would be the bad alloc here, which is a bad allocation. So this just says can be thrown by new, which is true, but not very specific. So bad allocation happens when there's not enough memory to actually allocate what you need. So in the context of this program, which it happened for some of you, and then some of you it didn't actually end up throwing it, which might just be dependent on the system and runtime environment. Actually, not the runtime environment, the system. Was we allocated an array that was just some really big number, so it was like 1 billion, and it was unsigned long. It was like 1 billion integers or something like that, and so that might not fit into your memory, and either you don't have enough RAM on your computer to accommodate that just in general, or the program itself doesn't have enough memory, so the operating system actually gives programs memory as they're running, so it can manage, not giving too much memory to one program and not enough memory to another one. So if your program itself does not have enough memory to do that allocation, whether it be a really big array like in the program, or even a class type if you're just using that much memory, then it's going to throw that bad allocation error. And so you don't throw that yourself, at least you probably shouldn't. That is thrown by the new operator when it cannot do the allocation. So we have some of these other ones. Logic error shows up quite frequently. It's somewhat true. It's if you have something that doesn't really make sense semantically, it will usually throw it. That one, I can't remember where C++ throws it the most, but you'll see this one a fair amount. Let's see, invalid argument I think gets thrown a lot. This one wasn't in the assignment, but I think it's important to bring up. Invalid argument gets thrown when an argument that you provided to a function is not correct. So a lot of you have gotten that from S to I. So S to I is a function that converts a string to an integer. But that doesn't work if the thing is not an integer. So if I wrote this, then that's going to throw a bad alloc. Or not bad, sorry, bad argument. And then if I, called it with something else, like a line feed or something like that, it's not going to be able to work either. And I'm sure there are other functions that throw it too, but if you provide something that just doesn't make sense for it to work with, it'll throw that bad argument. So generally, that would be functions that take a string and then parse it and turn it into something else, so s2i or s2d, or possibly some other ones. Then it's going to throw a bad argument because you gave it something that it can't really work with. Right, so that one you didn't need to catch in this assignment, but it shows up so often that I figured I'd mention it. Out of range error gets thrown when you go out of range of an index. Usually I'll just say segfault when you run on Sally for some reason. Actually, no, that is what it is. It is a segfault, but it is an out of range exception. Length error is called so this one says when a string is too big, but this can also get thrown if you allocate something that's not the right length. So I think this gets thrown in the context of the program if you try to allocate a vector that is bigger than your current vector, because then you're creating extra length that shouldn't be there. So yeah, that one can get thrown a number of ways. It has to do with the length of arrays or things that are array-like, which a string, I suppose, is, so that's okay. And then a overflow error, I guess, would show up if you did some floating point arithmetic. So if you're familiar with your CPE 101 stuff, an overflow is just when you have too big of a number to fit into a register, and then the bits start to overflow out of the actual number, and they can't fit anymore, so that would be that one. That would show up if you're adding really, really big numbers, like integers, and you just add a lot of them, then that might happen. You can also have an underflow error, which would typically happen when you have floating point arithmetic. If you did a whole bunch of multiplication by floats, then you probably remember from math that when you multiply decimals, they get smaller, so if you do that too many times, you might start losing some bits to underflow because it comes too small. Right, so I just wanted to bring those up, and then the big file exception and all of that were things that you had to handle in that assignment. Last thing to mention on this before we get to the review is that you can throw, so I didn't know this when we actually did the exception, which is why I didn't talk about it. You can throw things that aren't exceptions in C++, which I think is a little bit strange from an object-oriented point of view, but I guess makes sense in the context of C++ because exceptions I don't think are built into the language. They're just a extra class there, and I assume that just has something to do with the fact that it's built off of C. Although I imagine C has exceptions as well. So what you're allowed to do, and a lot of you have figured this out already, is you could throw something like, so if I had a string, so there's that read file function, right? Void, well actually it probably returns something, but void refile string file name. Then if you end up encountering an error, you can also throw primitive data types like integers or file name, or sorry, strings, which would be the file name here, or whatever that you want. And those aren't actually exception types, so they don't inherit from exception, which means that they shouldn't get caught if you try to catch an exception. That's just, exception. But yeah, you can throw strings and integers at bare minimum, which I think is strange, but I guess it's there. So you do have that option, and that's how you should handle the big file error, I think. No, sorry, that was an integer. The big file one, you want to throw an integer. The couldn't open one, you want to throw a file name, which is a string, in the assignment. So that's something I didn't mention. That was in the assignments, and I think most of you figured it out without me having to bring it up. But I didn't actually talk about that because I didn't realize it was a thing. Right. So I think that's about all I wanted to mention for those exceptions. I just wanted to make sure that we're at least a little bit familiar with some of them. So any questions on that? And if not, was there anything that you wanted to talk about specifically for the review? And I'll maybe pull up in the syllabus so that you can see the topics again. Alright, so any questions in particular, anything that you guys want to cover that has to do with the part 6 there to part 10, which is what's going to be on the final? And also one other thing, we're still writing the final, so I don't know all the questions that are going to be on there right now, but I would say that with the ones I've written so far, you might want to look at the write-ups. That might help a little bit. Some of the questions are very similar to that. I'll at least say that. So if nobody has any specific things they want to go over, maybe we'll just do a little bit of everything and see what we have time for. But if you have specific questions, I guess throw them out, or something you want in particular. I guess we'll just start with reminding ourselves about abstract classes and virtual functions, and then we'll just kind of work our way down and see what we have time for. So I think that's the new button right there. Right, so we'll just remind ourselves an abstract class is a class that cannot be instantiated. So the example we usually went with at the beginning of the semester was if I have some sort of game where everything in it is a game object class, so I can inherit from that and create things like a player or a enemy or an item or whatever you want, then these things might be abstract, specifically this one, maybe even this one too. I would probably say I would implement as abstract if I was actually writing a game. And the reason I would do that is because I would continue to do more with it. So I would say maybe we have like a jumping enemy, and then maybe like a walking enemy or something like that are more specific. So the idea behind an abstract class was if the thing you want is not specific enough, you want to extend it further and you want to make it more specific, then it should probably be abstract, which means that I cannot instantiate it. So in the context of my game, an individual thing in the game might be a player or an enemy, or some specific type of enemy, or it might be an item like a coin or key or whatever you decide to go with. But those are very specific. Those are things that are in the game, and you would never say that they're just specifically a game object and that's it, because that's not specific enough to describe them. In which case, we shouldn't be able to instantiate something that is just a game object, because we want it to have more. We want it to be more specific. And so the way we did that was we would write a class that had a abstract function in it. So if I did a class game object, then I needed to make something abstract. Or pure virtual was the other word for it. So I might have something like update, which updates the game object every frame of the game, and that would be, so an abstract, and the reason they call it a pure virtual in C++ has to be virtual by definition. And then what we did was we gave the normal declaration of it, and then just for the body we said equals 0. And so that would make it abstract. Or pure virtual. And then we said what the virtual keyword meant was it means that it can be overridden. And I think with some of the questions I've been seeing, they've been kind of focusing on the fact that there's like an override versus an overload, which I guess, yeah, is a thing. So we override virtual functions, which means we make them completely new. We remove the old one, right? So here, if I make a virtual function, then what that means is that if I ever inherit from the class that contains the virtual one, so if I made a player class that inherited from game object, and I meant to put public here, just pretend it's there, public, and then if I go down a little bit, then I can re-implement any sort of virtual function. So I could write, scroll that up a little bit, I could write a void update and then actually write some sort of body here, dot, dot, dot. And now, whenever I call update using the player class, it will always use this one over that one, right? And that will happen only if it's virtual. So if it's virtual, it will always use the overridden version, which completely destroys, or not destroys, but it completely overshadows the one in the game object version. So I can still call it. Remember, if I wanted to, I can specify like this. So it would have to be in the context of a function, right? I could say like game obj : update, and then that will call the base class version. So I have to specify what update I want now if I want to call the one that I've overridden. But what it will do is overshadow it, and any time that I call update, it will know specifically I'm referring to the player one if I'm using a player object. And that is what virtual means, is I have the ability to do that override, to overshadow any sort of code that was virtual in the base class. Whereas if I don't mark it as virtual, it will try to call the base class one even if you don't want it to, which is maybe not the intended behavior. So a lot of the time I would recommend writing a virtual function if you ever intend on implementing a function of the same name in a derived class. And so I guess last thing to mention on that would be that overridden means the ability to do that overshadowing, completely make a new version of it that takes its place, whereas overloading, right, was if I have two functions of the same name. So an example of overloading would be if I had, let's just say, a integer function called lookup, and one time it takes nothing, and then another time it takes like an integer index. I don't know what this would do exactly, but right, an overload is when we have functions of the same name and they do different things potentially if you give them different argument lists. So this one takes nothing and this one takes an integer. So that's the difference between an overload and an override, since I realized some of the questions might be about that. And an overload is things of the same name with different parameter lists. An override is taking a virtual function and overshadowing it and changing its behavior. Any questions on that abstract or virtual stuff? Just a brief overview of what we talked about before. Right, so the next thing was operator overloading. Not a whole lot to talk about with that, I would say. But just remember, what was the purpose of operator overloading again? Does anybody remember? Because I almost guarantee you that will be on the tests, even if I haven't written it yet. I'm sure somebody will put it on there. So if I had maybe like a fraction class. down to main. So with fractions, maybe it makes sense to be able to write something like this, where we say fraction 1 we'll write a question from assignment 8 and 9 be on test 2. Probably. Assignment 8. I need to remember what that was. So assignment 8 is the exception one, right? So I haven't seen any from that yet, but I would definitely count on it. Assignment 9, I can tell you that there are questions that have to do with the write-up on that one. Although assignment 9 isn't due for a while. I think I have it due before the test, but I might end up extending it, especially given everything. So 8, maybe I'll post the answers after it's due, which is now Wednesday. I extended it to, and we don't have class, so unfortunately I can't just give it to you. So maybe I'll just post some answers to that so that you have the idea. Assignment 9, you know, if you're confused on it, just send me some sort of message. But there will definitely be questions regarding those. Right, so if I wanted to make a fraction class that had something like this, then if I wanted to add these two things, so let's just say fraction f3 is going to be fraction 1 and fraction 2 added together, then I maybe want to write something like this, right? Because there's kind of some sort of common sense interpretation of what adding two fractions means from, you know, just normal math, right? It means that we find a common denominator, we add the numerators together after that, and then, you know, maybe simplify or something like that. So fractions are not built into any language, but we maybe want to be able to add them as if they were. So the advantage of operator overloading is that we end up getting something that's more readable and looks like normal mathematical notation. So, you know, common examples of that might be the fraction class that I kept writing, or, you know, maybe if where I end up using it a lot because of, you know, a lot of the programs I write is I'll write a class called matrix. So it's like a matrix from math that takes doubles, I guess, and then has an array. So we'll just say something like weights, I guess, would make sense for that. And that would be a 2D. Right, so in math, you might have like a matrix A and a matrix B, and if I write those as classes, maybe I still want to be able to use them. And so in math, right, there's a difference between multiplying A by B and B by A, and if you remember from like your high school math, the idea was that we have to match the inner dimensions of these, and then we multiply each row by each column. Well, actually, yeah, I guess it would have to multiply by each column. So we'd have to do something like that. And we can write a matrix class that works like that. So I could declare a matrix A and a matrix B and just do A times B, rather than having to write a whole function that doesn't look as nice that multiplies them. And, you know, you could do scalar multiplication with matrices, right? So I could do something like this. That's pretty normal for math. So, you know, you could rewrite these classes, generally mathematical ones, and have them look nicer just because you can use these normal math operations on them. Or you can also overload your classes to use the insertion and extraction operators, right? So I don't want to do that. What was the class from the operator overloading one? It was... I just created this last week. What was the class from the operator overloading one? Big num, right? So that one was, if we had a big num, and we initialize it to some actual value here, then what I was allowed to do was say something like this too. So even if I'm not strictly using it for math, in this case I guess we were again, I can override something like the extraction or insertion operators and make it so that it just prints it and I can write it normally. And again, this is just more readable than writing something that says like a dot print values or something like that. Then maybe I could write a function that prints this and then also put that same code into the extraction operator, and it's just slightly nicer to look at the first line here than it is the second line, and that's really the only reason we use operator overloading. So be careful, because I see a response a lot is that it makes things faster, which is not true. Same overhead regardless. A operator overload is still a function call. In fact, it's basically the same thing as this. It's just predefined to have some specific arguments because it's an operator that we expect to be, binary or unary or maybe even ternary. It is the same as a function call. It's just, it looks nicer. It's written in a slightly different way. So just be careful with that. The only advantage to operator overloading is that it's more readable. Just nicer to look at. No other reason that we write it. Any other questions on that one? Okay, let's go back, look at this one. So the other part was the exception handling, which we talked a bit about earlier. It's back. There we go. So exception handling is just these try-catch blocks, right? So you try to execute some code, and if you encounter an exception inside of it, you can catch it without the program crashing. And we can have multiple catches that are able to catch different exceptions. So I might have something where I do array -1, and that's not valid, right? I can't go to the -1th index of an array, so I might have something like an out of range exception here. And so remember, what you do is you specify, so you basically just do a declaration. So I say, if I happen to encounter an out of range exception, let's create a new variable for it called E, and then I can do whatever with it. So I could say something like cout out of range. And then remember that the exception classes have a field called what, which is actually a function call in C++, but it tells you what exactly the exception was. So here, the out of range exception might get thrown if I had a line like that. And then you also had the ability to throw exceptions on your own. So I could do some sort of check usually, but I can throw some sort of new exception. So I could throw my own exception like this, and then say, give it a string, and say this is an exception or something like that. And then I can catch those as well. Right? So whenever you throw it, whether you explicitly throw it, so this is a line where I would explicitly throw an exception versus whether a library or a function that you're using throws it, it will always look for which exception matches us the best. So if I was to execute this code, it would always throw this one, right? Because it comes first, unless I like comment it out. So it would always go and catch this out of range one, because that's which exception this one is, right? This is an out of range exception because it's not in the range of the array. Versus if I threw this one, it would go into this block here. So just remember, if you ever throw an exception, it immediately stops the execution of whatever you're doing, jumps out of it, and goes straight to the catch block. The reason you use a try and catch is if you have unsafe code that you're unsure is going to work and you think it might throw an exception, you use it to make sure that your program doesn't crash and just stop running. So it will stop executing that unsafe code because the code in it is no longer safe if you have an exception. Because if I did something like this, right, and maybe used array later, then I would hope I'm not using whatever value is at the -1 position because it doesn't exist. So I can't be guaranteed that my actual code is going to work, right? At that point, I need to break out of the try block. I end up in some sort of catch that catches it, and it will execute from there and not do the rest of the try, right? So you put unsafe code in there. If you don't want that code to run in the event that you get an exception, you put it in the try block. The catch block handles what you want to happen instead if you were to encounter that exception, right? And so all it does is look for which exception best matches it and finds the first one that does and then uses that catch block. So any questions on that one either? I know the assignment's due on Wednesday for this one, so if you have any questions about it still, now might be a good time to ask. They can be useful for debugging. I guess they're more for when you're uncertain of what's going to happen. So I typically use them if I don't know what the result of a function is going to be, whether it be like an external library and I just don't know how the function works because their code isn't public, or what I usually use it for is so I do like app development usually. If I make a call to a server and I'm unsure if I'm going to even get a response, so maybe, in this case, maybe if I'm debugging a server-side script and I'm not sure that the thing it's going to return is correct, then I might use an exception so that my program doesn't crash, but I can still keep running even if the response isn't good. So maybe if you write a function that's very complicated and you're unsure that it's going to work every single time, you might just put a try and then some sort of print just to make sure that your program doesn't crash, but it still addresses the fact that you had an error and it tells you, so that you can keep going with it. So it is kind of useful for debugging. It's really just there if you expect to have an error, but you don't want your program to crash. So if you're rolling something out for production for somebody to use, it's maybe a good idea to put a try catch block there so that when inevitably you program a bug, because I'm sure we all do that from time to time, it doesn't crash on the user. It won't do anything for them probably if you don't catch the exception, or like do some specific handling. But then they don't know that your program doesn't work as much. They just get some sort of minor bug instead of the whole thing just breaking and crashing, and then they give you a bad review or something like that. It's really just there to prevent crashes. Although you can find useful things for it too. You can intentionally throw an exception if you really want to. You can kind of be lazy about things and not do any error checking and then just say, if I get an exception, then we'll handle it later. So maybe if I'm not feeling like parsing something and I try to call it with S2I, I could just catch invalid argument error, and then just say, move on with it and throw out the data or something. Any other questions on this? Okay. I'll pull this one up. Got about 20 minutes left. I'll try to get through these two. We just talked about linked lists recently, so maybe I'll just leave that one. Right. So, what was it again? It was templates, right? Just remember that a template is basically just a class or a function where you can fill in the type later. So in your declaration, you put template, and then class, and then whatever the name of the type, and you can put multiple of these, even though we haven't been doing it. You could make multiple generic types if you wanted to, and that would be okay if you just need to use multiple of those. I think in general, I don't really ever find myself needing that, but maybe you would for key value pairs or something like that. Let's see, so we can declare some sort of class, let's just say example, and what a template lets me do is fill in that type later. So I might here have like an array, so a t pointer. So I can use this type anywhere inside of the scope that it is defined for. So here it's for a class, so I can use this generic type anywhere, and then it will fill it in later. So if I do something like this, it will now use an array of whatever type t happens to be, which we'll find out later. So if I was to write later in the code, integer main, like that, and then I say, so I wrote an example class, and I would say it wants to be an integer version. So we use these curly brace, or not curly braces, these angle brackets to specify what the type is, right? And then just E, kind of like how you've been doing with vectors, because that is a template class. And then I could maybe create another example class that takes booleans. We'll call this one B, I guess. Then what the compiler does is it goes and looks up here and it says, okay, the generic type you wanted was T, and it goes and physically replaces all of the places it sees T in your code. So maybe I have more here where I have like a T returning function called foo. Returns something, maybe returns like R0 or something random like that. Then anywhere it sees that generic type T, it will go and replace it and generate the code for it. So when I write this here, it knows at some point I'm going to use an integer version of example. So it will go and basically copy paste this code. It will just take all of it, put it over here, and then it will just say, okay, T, that's an integer now. And so it will replace all of those instances of T with an integer and generate the code that corresponds to that. So the important thing to consider about a template is it actually does go and generate that code for you. It doesn't just kind of fill it in at runtime. It will physically copy and paste this and just return or replace all of the generic types with whatever it is that you want. So when I write this Boolean one here, it will also say, oh, you're going to use a Boolean version at some point? Well, okay, I'll go generate the code for that too. And so it will go up here and generate another version of the class where all of the T's here have been turned into Booleans as well. So we'll go physically generate those code, and it will only do it for the ones that you use. So once it sees that you have used that specific version of a generic type, it will say, okay, I'll go generate code where I replace that, if I haven't done that already. And so, it might generate multiple if you had multiple generic types up here, where I could do different combinations of like integer, Boolean, Boolean character, all that kind of stuff. And I could do this for functions as well, right? So I could declare a template function that takes a specific thing, which maybe I'll write in a second. So just to clarify the terms, because I did see a bit of confusion, I think, on the write-up for this one. This is a template. So the class or function that is being made to use this sort of approach, that's the template part. This part right here, that's the generic type. So this is the name of that. It's generic type. So the type itself, T or type or whatever you use, that's not the template. The template's the whole thing. The type is a generic type, is the term for that. Right. So the last thing we maybe wanted to say was that I can apply it to either a class here, in which case it applies to everything in the class, has access to that type T, but I can also define it for a function, which can also be part of a class, I suppose. And let's just call this one U. So I could say like void bar. And now I can use some variable U in here, or I could return it, or I could even put it as a parameter as well. So I could say U variable or whatever, and so I could say like UX. And again, it will just go and generate that function for whenever you call it using that thing. So if I was up here in main, then I would probably have to call this like bar, let's just say float. And then like 3.4, since it also takes a float. Right, so again, we have to specify with those angle brackets whenever we use something that is a template, whether it be a class or a function. If that thing specifically is marked as a template, then I have to do that. So the common example of this was sorting, right? Because I can sort booleans and floats and integers and strings and all of those different things, and maybe I don't want to write bubble sort a million times for each of those, so I can just write a generic type that does bubble sort, and then the compiler will go and fill it in for you later. Any questions on template classes or generics? Okay, I will go to this one. So invariance I don't think will actually be on the test, so just heads up on that. That was just something I wanted to talk about because I felt like it fit in. So let's talk about recursion for a moment. Right, so the common example we've been doing for recursion was something like factorial. So if I had 5 factorial, then remember this is 5 times 4 times 3 times 2 times 1. And something like 4 factorial is 4 times 3 times 2 times 1. And the thing we noticed was, well, this part right here is the same as 5 factorial, and then something like this part here, that is 3 factorial, right? 3 times 2 times 1. So what we figured out was, oh, well, any factorial seems to be the number itself times the factorial of the number underneath it. And so what we could do is use these previous solutions, or smaller in scale solutions, and apply them to our new part. So if I wanted to write a thing that took factorial, so int factorial of n, then what I needed to do was call something where I say n times the factorial of n minus 1. which was the pattern that we noticed here, right, was that it's n, which is whatever the number, and then times the factorial 1 less than it. And so that's the way we could do it recursively. So the actual recursive part was this here, right? So this was a call to the own function that we are currently inside of. So I can call factorial within factorial itself. And that's the recursion part, is the ability to actually use a previous state of the same thing to solve a problem. And then remember that there was another two things we needed. So does anybody remember what the two things that we need in order for our recursion to work would be? So maybe write this out a little bit more. So there was always some example that wasn't in terms of any of the other solutions. And we kind of always have to have that because there needs to be some sort of primitive, definition, at least one, in your like space of math that you're working with, right? So we needed a place to stop at. Here, and then we also needed a way, if we started at 5 factorial, to work our way down, right, and be able to look at the previous ones. So remember that the two things we needed, so I didn't write the code for this part here, but by definition, right, I would need to maybe mention that if n equals 0, then 0 factorial by definition is 1, and I can't go any lower than 0 factorial, so I should stop there. So we need some sort of stopping point, otherwise our code is going to recurse on itself forever and keep calling and calling and calling and never stop. And we also need some way to be able to go down a level. So here we go down something, or in other words, we make our problem smaller so that it actually approaches that stopping point. Right, so the two parts of this, again, were the base case, which is that stopping point. It's a thing that's defined that we shouldn't go any smaller than. And then we also had something like this, so the n minus 1, right? If I do a subtraction by 1, then that would make it smaller. So the number that I'm taking factorial of, if it was like 5, this would be 4, and then when I call it 4, it would be 3, and then 2, and then 1. And so it starts to approach that 0, which I know is my base case. So I need some sort of reduction operation to approach my base case, which is just a way to approach, right? And so it doesn't always actually even necessarily have to make it smaller. It just needs to approach it in some way. But we usually say reduction because I think it makes more sense to go from bigger to smaller than it does to go the other way around. And typically you need more information if you are making something bigger. So generally you want to reduce it, whether that be subtraction here, where we're subtracting the size of the factorial, or where we did sorting, where we made the size of the list smaller, so that wasn't necessarily subtracting, but reducing the space that we're working on. We could also do, so I know I mentioned quicksort and merge sort earlier in potential topics that we could talk about. What that does on an array, in just the most plain, vague terms, is it will split the list into two different parts and then call itself on both of them. So it would do merge sort here and then merge sort here, and these would both be recursive calls. And so it'll keep doing that until it reaches a block of size 0. So in that case, it's not really subtraction by 1, right? It's cutting it in half. But it's still making it smaller. It's a reduction operation. What were some other examples that we had? Right, so we could subtract by 1, we could divide and make it smaller, we could cut the actual physical space down. Just, some way that makes it approach some sort of base case, I guess. So the main takeaways from this: a recursive call is one that calls the own function that you're inside of, and in order for it to work, it needs a base case, which is a stopping point, and a reduction operation, which is the thing that makes it approach that stopping point. Any questions on the recursion part? Okay, then last thing to review is the linked lists. And you don't need to know the doubly linked lists for the exam. I don't think that'll just be on the next one. Although it's not all that much different if you remember. So linked lists, right, where lists where we have some sort of data and then we have a pointer to the next thing in the list. Until we reach the end of the list, in which case we just say that the pointer points nowhere, right? Just to do that. Oh, is the reduction operation always used within the return? Good question. So not necessarily. So the way I might do merge sort, which again we haven't talked about, but we'll just talk about the general idea behind it, is I take some sort of array and then I need to work on both halves of these, and part of the reason it's called merge sort is I have to take these lists and kind of merge them into a new one, in which case I need to make like a copy of the array itself. So I either need to make a copy of this whole array or make a copy of both halves individually and then work with those later, is the gist of that algorithm, even though we don't necessarily know what it is, so maybe I'm just talking about some nebulous concept here, but if I do that, then maybe what I would do is I would create two new, so let's just say I'm sorting a list of vectors, or a vector called list, so a vector of some type t. Then what I might do is I might make something called like L list, which is the left list, and then make it just part of the vector, and split it up in that way, and then also do it that way. So the actual reduction here is making the list smaller, right? And in some way I would like either copy this or use a sublist function that's in whatever language it is. But I guess what I need to do in order to reduce this is break it up into smaller parts, and I can physically do that by just putting the memory into a new variable and making a copy of it. In that case, it's not actually in the return statement, right? I'm doing the reduction here, and then I would return, I don't know how I got all the way over here. Is this even the same slide? I'm not sure what I clicked to get over there. Oh well, whatever. But here I would return, actually I guess it's void returning. In that case, I can think of an easier example. So I would sort the left list and the right list recursively here, and then I would return. I'd actually need to merge them, I guess, too. So I need to do more code down here that does stuff. But here, the reduction is actually, I guess, above it. A better or simpler example I just realized would be if I just said void print list. I guess I would need a list there too. So if I was printing a list and doing it recursively, then I would see out list sub I. And then there's no return statement here at all, right? Because it's void. I would just call print list. I need a base case. I'm just forgetting it, but I would call it with I minus 1 and then call it with the same list, right? So here I don't even return anything. So that's not even necessarily the case. So it needs to be reduced somewhere and then passed as a parameter. So the parameter itself passed to the recursive call, that needs to be reduced in some way. You can either do it inline here, which is what I typically do to save space, or you can do it in multiple lines like I might do with merge sort, which I'm just kind of waving my hands and saying this is how it would go if we knew what it did. But yeah, so you don't necessarily have to do it in the recursive call itself, and you don't need a return statement because you can always have a void recursive function call as well. If it just does something like printing or traversing a list, maybe is a common example in languages that actually use recursion. Right. So I don't know how this all got rearranged like this. I wonder if it made multiple copies of it. I don't really know. So they're not, right, you would need to pass some sort of reduced parameter. But just consider, like, I could always just say int x equals I minus 1, and then just do this instead, right? Which is inefficient, but, I mean, it does the same thing. But you need to pass a reduced parameter in some fashion to the function. Where you do that, I guess, is up to you, but if I can do it, I do it in the inline in the parameter call itself, or a parameter list, I guess. I guess it's argument list. We're being pedantic. So last thing on this one, we'll just talk about linked lists really quick, which we talked about the last 2 weeks, so hopefully you remember it. Unfortunately, we won't have a programming assignment on it until I think assignment 10 is linked lists, and then assignment 11 is the final. I was re-looking over things. I think that's what it's going to be. So unfortunately, I don't think you're going to have an assignment on it until much later, but linked list, right, is where we have data, and then basically it was like an array, but instead of everything being right next to each other, we just have it point to the next thing. So we had a node class, right, and that class had data of some kind, and then it had a pointer. So it had a node pointer. So I'll just say T for generic type, a node pointer to the next pointer. And it would keep going until it hit one where it wasn't pointing to anything. In other words, it was pointing to null. And so there were 3 things that we worried about with most data structures, and that we had here, which was the insertion, the lookup or search, and the deletion. So just very briefly, remember that the insertion, what that did was it would follow each of these next pointers. Maybe it even looks a little bit better that way. It would follow each of these next pointers until it reached the end, and then it would put a new node here at the end, right? It would go here, make this one null, and then make this one point to that one, so that we can put a new thing at the end. And then remember that the only thing, which we kind of had to use as a starting point for this, was the head pointer, which always pointed to the beginning of the list. So that was the insertion. We follow each of these pointers until we reach a point where the ending was null, and then we change that to be null to point to a new pointer so that it ends up at the end of the list. Remember the lookup was basically just the same thing. We just followed it until we hit either data that matched the one that we're looking for, or if it was a specific index into the list as well, we could just follow the pointer that many times. So remember, if this was like index 0, 1, and 2, then I follow the pointer 0 times to end up at index 0, 1 time to end up at index 1, and 2 times to end up at index 2, and etc. for those ones. And then the last part was deletion, which, remember, again, we do the same sort of thing as far as arriving to the actual location. So we just follow the pointers till we get to wherever the thing is we want to delete. In this case, we said unless we're using recursion, we had to keep a pointer to the previous one and then the current one that we want to delete. And what we would do is we would redirect this pointer around the current one so that it's successfully severed from the list, and then we would delete it so that we didn't lose any sort of information before deleting it, right? So we would cut this tie, make it go around it, and then actually sever it. And we always had to keep that previous to be able to make the pointer go around it unless we were specifically using recursion. And then the other things that we just had to address were if we, deleted a head or inserted when there was no head, then we need to either remake the head and make it point somewhere else if we're deleting the head, because then we're losing it. Or if we are inserting and we don't have a head, we need to make the current insertion a head because we don't have anything. Okay, so I think tried to get through everything. Hopefully that wasn't too fast. Any final questions before we stop here? Okay, so no class on Wednesday, but the exception assignment 8 is due on Wednesday, so just make sure you get that done. And then assignment 9 is due soon. The exam is next Monday, so it'll be normal class time. We don't have to show up, so just so you have more time, you can go straight to Canvas, take the exam. If you have any questions, just send me a DM on Discord or a message on Canvas or email, or whichever is easiest for you. And I guess I will see you all next Wednesday.